Analytical Chemistry 2.1 by David Harvey. This is the text that we will be using. The analytical chemistry is a quantitative science, whether determining the concentration of a species, evaluating an equilibrium constant, measuring a reaction rate. So the analytical chemists engage in measuring important chemical things. So we measure things. In this section, we review briefly the basic units of measurements. So a measurement usually consists of a unit and a number that expresses the quantity of the unit. We can express the same physical measurement with different units, and most of the time creating confusion if we are not careful to specify the unit. For example, the mass of a sandball that weighs 1.5 gram is equivalent to 0.0033 pounds or to 0.053 ounces. To ensure consistency and to avoid problems, scientists use the common set of fundamental base units. So we will see the list of that in a table. So these units are called SI units after the System International unit, so International Unit System. Now we define other measurements using these fundamental SI units. There are 7 base units, but there are also derived units. So one of those derived units is joules, for example, where joules is equivalent to meter squared times kilogram divided by second squared. In this table 2.1 in Harvey's textbook, as you see, we got mass. The unit of mass is kilogram with the symbol of kg, lowercase. The definition is here. You can read that. I'm not going to go over that. You can pause the video and read all the definitions. The second fundamental unit measurement is distance. The unit is meter, and the symbol is m. The temperature is Kelvin with capital K. Time is second with lowercase s. Current, the amount of substance, and light. These are 7 base units. And all the other units, some of them are listed in this table, are derived units. And here there are some derived SI units and non-SI units. For example, this angstrom is a non-SI unit. It equals to 10 to negative 10 meters. Volume, for example, we get liter. It is also non-SI unit. So liter equals to 10 to negative third cubic meters, or it is 1 liter equals to 1 cubic decimeter. We got force, we got pressure, we got energy like joule, calorie, electron volt, and this unit here, whenever we want to convert from joules to calorie or calorie to joules, we can use this equivalency or as conversion factor, of course. We got power, for example, watts, and watts, as we know, is joules per second, and joules is meters per second, meters square times kilogram, so it becomes a second cubed. And so these are basically the units that are derived other than the base units. Now, chemists frequently work with measurements that are very large or very small. For example, a mole of anything consists of this many particles, this many ions or molecules, in short particles, and that is a huge number. And there are some analytical techniques that can detect very little substance. For example, that is really small number mass of a compound. So, and most of the time, if we deal with these numbers, it is really challenging to keep them correct, because we have to keep counting the numbers, the number of zeros especially. So that's why, for simplicity, we express these measurements using scientific notation. And for example, for this Avogadro's number, instead of putting many zeros after the non-zero decimals, we can write 6.022 10 to 23rd. Of course, we got some additional digits there, but most of the time, that's what we use. And the other numbers, when you move the decimal point to the right, so you come up with 15, so that means we have to move 15 times. So as you see, it is easier. The scientific notation makes it easier to handle the numbers. And instead of putting those zeros and keep counting them, we can use scientific notation. And sometimes we wish to express a measurement without the exponential term. We can substitute the exponential term for a prefix. For example, in prefix table here, we got from Yato to Yacto, and this huge range from 10 to 24th to 10 to negative 24th. And so 10 to negative 15 gram, so that is the exponential term. We can substitute that for a small letter prefix, femto. So you see the whole thing. Now here, this huge number here, we could simplify it as 1 times 10 to negative 15, but we can further simplify it or make it better or more useful, or to handle it easier. We can substitute this 10 to negative 15th, as you see it here, is femto. Femto, the symbol is F, so it is 1 Fg. So that 1 Fg femtogram represents this number here. This number here. So it is easier to handle. So the prefixes makes it really easy, makes analytical chemist job very easy. Now, so you see Yata here. So the it's 10 to 24th. It's like putting 24 zeros after one. That's a huge number. All the way down to Yakta here. So you got 24 zeros before 1. So this is really small, from very large to very small. And between we got other prefixes, of course. Something we need to notice that the first in this column here, up to mega, down to mega, we use capital letters for the symbol. And from kilo and on down up to Yakta, we got lowercase symbols. And except for the deca, they are single letters. They are single letters. So you see all of them. And here, one way to keep in mind or kind of memorize is to use mnemonics here. From top to always down, all the way down, we can come up with. I got this from internet. A young Zach earns pennies to give mighty King Henry's daughter, Beth, who drinks cold milk until 9 p.m. for a zillion years. So that's kind of a it's nice way of memorizing all those prefixes, and most of the time, as you see, we have base here, base. So base could be meter, could be uh, could be second, liter, second, liter. So let's write meter again, and so on. So it could be any unit. So that is the base unit, and then we have a smaller scaled prefixes and larger scale. So we can simplify. We can handle the numbers very well with these symbols. And sometimes, for example, if you want to convert micro to nano or vice versa, you don't have to go from micro to base and then from base to nano. So we can see, you see the difference. The micro is 10 to negative 6, meaning 1 micro, let's say liter, equals to 10 to negative 6 liters. Meaning if you have a million, if you split a liter into million pieces, so each piece is called micro. And so the nano, 1 nanoliter is 10 to negative 9 liters. So similarly, if you split a liter of solution into billion equal volumes, so each volume will be nanoliter. Now, the difference between this here is, as you see, the negative 6, negative 9, which is nanoliter, and you come up with, so this will be plus, so negative 6 plus 9, that is 3. That means 1 microliter equals to 1,000 nanoliters. So if you want to convert any value, let's say 25 microliters to nanoliters, you can use this conversion factor, this equality to conversion factor. Let's do a real quick one, 25 microliter. And so we know 1 microliter is 1,000 nanoliters. So that will be 25 times 10 to third nanoliters. Of course, most of the time we move this decimal point to make it scientific notation. So when you move from right to left, you add 1 because you are making the number 10 times smaller. And so you have to make the exponent 10 times larger. So that will be 2.5 10 to 4th nanoliters. Yeah, we'll have some examples. For example, here we got some example. Write the prefix and the symbol for the following factors. 10 to 9th. If you look at the table here, 10 to 9 is giga. So we write giga, and we don't have to, with capital G. But this symbol is capital G. 10 to 24th is here. And that is capital Y, capital Y. 10 to 15 is peta, and the capital symbol is capital P. 10 to negative 21st, zeta, and so that's lowercase z. 10 to negative 12, as you see, negative 12 is pico, pico, lowercase p, 10 to third, that's kilo, lowercase k, 10 to negative 15th is femto, lowercase f, 10 to negative 9 is nano, as you see, and the symbol is lowercase n, nano, lowercase n. We can kind of practice on this to memorize them. And here we substitute the exponential term in each of the following for appropriate prefixes. The first one is I already done it. So 10 to negative 13 is close to femto. It's close to femto here, as you see. So 1 femtojoule, so that's 2.0 10 to negative 13 joules, and we want to show it in a better way to get rid of the exponential term and to replace it with a prefix and make the number more easily handleable, or that can handle, manageable. So we can use this 1 femto is 10 to negative 15th joules. 1 femtojoule is 10 to 15. So we have here the reason we put joules denominator so that we can cancel out. So joules is gone. What is left is femtojoules. And so here we got an exponential in a denominator. Here we got 10 to negative 13. So your number will be 2.0 10 to negative 13 minus 15. So that's how you handle it, the denominator. So you subtract it basically because we got 2 zeros here. That will become positive. So now you got positive 15, negative 13, and you come up with 2.0 10 to second femtojoules. And 10 to 2 means 100. You multiply the 2.0 by 100, so you come up with 200 femtojoules. That is your answer. So the 1.5 10 to 7 molar. How can we simplify this? How can we use prefix so that we show it better, basically? And I think the closest one would be maybe 9. We can use 10 to negative 9, nano. Let's try nanomolar if we can do that. And so we multiply it. Now the goal is to go from molarity to nanomolar, and that is so one nanomolar is 10 to negative 9 molar. That's the prefix what it, and here the molarity is cancelled out, and we got 1.5 times 10 to negative 7 minus 9. So this denominator here, and the unit is nanomolar. And now we can put 1.5 10 to negative, so this will be positive. So we got positive 9, negative, so it is 2. You got 2 nanomolar, and just multiply that by to convert it to decimal number. It will be multiplied by it, so it will be 150 nanomolar. nanomolar. If you do it for micro, for example, which is close to 10 to negative 7, you will come up with 0.15 micromolar. But I think this is a better number, I would say. So we got 3.98 10 to 14th hertz. That's frequency. And so 10 to 15th, I think if we like tera would be where is tera? Yeah, here. If we use that, so we can because 10 to 14th, we can use that one. Or peta, that is another, we can, so let's try tera. So 1 terahertz is 10 to 12 hertz. So hertz will cancel out, and you got 3.98 10 to 14th, and so you subtract 12, which is this here, from there, and you come up with 3.98 10 to 2, and so you will multiply it by 100 to make it decimal. So that's 2. So when you move from left to right, you basically subtract, you make this number here larger, then you will have to make the exponent smaller, and so that will be 398 10 to 0. So 10 to 0 is 1, and the unit is what? Terahertz. So that's, you see, comparing those two numbers, it is, so this is more manageable, or I mean, it's better number to have. So the other one, you can do the same thing. You can do the same with each of those numbers, and so I don't want to go over every number. So you can pause the video and go over, work on this one, 10 to negative 10. So maybe you can use a pico for a picometer, or this watts, for example, 10 to negative 13. You could use femto or pico, 10 to negative 20. You can try zepto and see how many zepto moles you will have. So work on these 3 exercises. Let's see what else we got. So here, write the prefix and the factor for the following units. What we mean here is, what is milli stands for. So milli, M, stands for when it is prefix, when it is used as prefix, is milli. If it is by itself, of course, it is meter. So we can write millijoule, and again, you can always substitute milli for 10 to negative third. So because milli, as you see it here, it means 10 to negative third. This is 25 femto watts. So femto watts is femto, we got here, that's 10 to, so 25 femto watt. So now we can substitute this femto, the prefix, for 10 to negative 15. So it will be 25 times 10 to negative 15 watt. So we can use capital W, that's watt. So again, it is reverse of what we've done in previous slides. N is nano, 57 nanosecond. And so this nano can be substituted, as you see here, 57 times to negative 9 seconds. This is kilo ohms, so 5.0 kilo ohm. And so kilo again stands for, could be substituted for 10 to third. That's ohm. This is deci, Pascal, this is microliter, this is zepto, and so on. So you can work on these three examples. So this is another example here, converting between metric prefixes. For example, if we have 150 sorry, this is a milli, that's milligram, and we want to convert it to microgram. So what can we do? The first thing is, there are several ways you can handle that, is by going step by step. We start with 150 milligram, and then we use conversion because we know 1 milligram is 10 to negative third grams. Milligram, 10 to negative third grams. So these milligrams will cancel out, and times we're not done yet because our goal is to go from milligram to microgram. So now, since we got gram left, what's the relationship between gram, which is base unit, and microgram? So as you see here, 1 microgram is 10 to negative 6 gram, and so that those grams will cancel out, and what is left is basically you got 150 times 10 to negative third, and then we got denominator 10 to negative 6, and so you just write 150 10 to negative third, this one minus negative 6, and so you come up with this is of course plus 6, this is negative 3, so you got 150 times 10 to third microgram. If you want to convert it to scientific notation, of course, it will be 1 point, so you will move the decimal point to the left twice. That means when you make the significant, this is called significant, smaller, in this case we're making smaller 100 times, then you will have to add 2 if you're moving to the left 2. So you will have to increase the exponent 100 times. So that is that it becomes 1.50 times 10 to 5th microgram. Now the second way, I mean, you can since we know the milligram, milli stands for 10 to third, so you substitute this m for 10 to negative third, so what is left is gram, right? So 150 times 10 to negative third, so we just replaced that m and gram, and then you so now we get gram. So what is a base? Gram is base unit, and so 1 microgram is 10 to negative 6. 1 microgram is 10 to negative 6 here. So you can so grams will cancel out, and now you got your microgram left. That is what we're looking for. And again, 150 10 to third microgram. And if you want to convert it to scientific notation, as we did it here, you can do that. And the another way is you look at the values for milli. That's negative 10 to negative third. Micro, the other one that we're trying to convert it to, that is 10 to negative 6. So what is the difference between those two? is 10 to negative third, the larger number, minus the smaller, which is negative 6. And so you got 10 to third left. That means 1 milligram equals to 10 to third microgram. So you can, in that case, once you find that, you can start with your what is given, 150 milligram, and we know 1 milligram is 10 to third microgram, so those milligrams will cancel out, and you come up with this number. Of course, if we want to convert it to a metric system, we can easily convert it there. Now this is from two extremes, 10 to 24 to 10 to negative 24, and so we can use this way here, 1.2. Well, let's find the difference between y, capital Y, that is 10 to 24, and the other one is 10 to minus 10 to 24, negative 24. So the total difference between those two extremes here, 10 to 48. That means 1 y, capital Y, m, equals to 10 to 48, and you can do the same thing here. So you start with 1.2 ym, and 1 ym equals to 10 to 48, lowercase ym equal to, so basically 1.2 10 to a huge number. So the thing here, we're trying to show how we can convert from one prefix to the other. So nano and femto here, nano is 10 to negative 9, femto is 10 to negative 15. So the difference is 9. That means 1 nanoliter equals to 10 to 9 femto FL, and so you can start 3.6 NL times, so we can use conversion factor here. So 1 NL is 10 to 9 FL, so NLs will cancel out, so what you have is 3.6 times 10 to 9 femtoliter. So that is your answer. So you can do the same thing here. This is micro. Micro again is 10 to negative 6. Kilo is 10 to third. So you're going from kilo here to micro here. And the difference here will be what? 10 to third minus the small one is 6. So you got 10 to 9. That means 1 kilosecond equals to a billion 10 to 9 microseconds. So you can 7.8 microseconds. So that is what we start with. And we know, so in this case, the micro has to be here, 10 to 9 microseconds, so that we can cancel out is 1 kiloseconds. And that 7.8. Now here, this the exponential in denominator, it will change the sign when it goes up. So it will go 10 to negative 9 kilosecond. Okay. Please practice on this. So here, another conversion between metric prefixes. So the question here is, during the 2010s, the average emission of carbon from burning fossil fuels on Earth was 8.45 petagrams of carbon per year. So petagrams carbon per year. So how many kilograms of carbon were placed in the atmosphere each year? So this is a simple conversion. Peta, and peta is 10 to 15th, and a kilo is 10 to 3rd, and the difference will be basically 10 to, so let's write it here. This is per capital, and that's 10 to 15, and kilo is 10 to 3rd. So when you take the difference, it will be 10 to 15 minus 3, that will be 10 to 12. So that means 1 petagram equals to 10 to 12 kilograms. So that is our equality, and we can use that equality as conversion factor. So we start with 8.45 pg, and so our conversion factor is 1 pg. It has to be denominator here so that we can cancel out, equals to 10 to 12 kilograms, and so you come up with 8.45 10 to 12 kilograms. That is your answer. Or if you want, you can use peta and then 2 grams from grams to kilograms. That is another way, but this is how we can solve it. So another question related to that: how many kilograms of carbon dioxide were placed in the atmosphere? So you see, the source of the carbon in this question is carbon dioxide, and so since we already found that we got 8.45 times 10 to 12 kilogram carbon, and we also know that the carbon dioxide, we got this is 12 gram, oxygen 16, that's 32 grams, total is 44.0 grams per mole. So the molar mass of carbon, that means in 44 grams of 44 grams of carbon dioxide, out of that 12 grams is carbon. So here the grams, we can cancel out those grams, and this carbon here, we can get rid of that, and what is left is, the unit is kilogram here, kilogram, and that will be 8.45. So you multiply, let me do the multiplication, bypassing again, writing that. So you multiply this number by 44 and keeping the exponential here, and divided by 12, you come up with 31.0 10 to 12 kilogram carbon dioxide. And of course, if you want to convert this to scientific notation, it becomes 3.1, 10, and of course you will increase the exponential exponent there. It becomes 10 to 13 kilogram carbon dioxide. So here we got, if we have 7.6 billion people, this is, I think, the population of Earth in 2018 or so, more or less. So if there were 7.6 billion people on Earth, how many kilograms of carbon dioxide were produced for each person or by each person? Now we know we just know how many carbon dioxide has been produced, to 10 to 13 kilogram carbon dioxide per 7.6 billion is 10 to negative 9th. Let's call it persons or people. And so if you do the math here, of course, you come up with, using your calculator, you come up with 4,079 kilogram per person. That's per year, I guess. Yeah, per year. That's too much, especially if you're smoking. Your contribution would be more. What else? Let's see what else we got. Converting areas and volumes. Now, the area, as we know, is length squared. The volume is length cubed. So if you have 2 times 2 centimeters times 2 centimeters, that will be 4 centimeters squared. So you multiply the numbers, but you also multiply the units, so it becomes centimeter times centimeter is centimeter squared. For cubes, you multiply 3 dimensions, length, width, and height, and 2 times 2 is 4, 2 times 4 is 8, so the volume is 8. And because you are multiplying 3 centimeters by it, it will be cubic centimeter. So the volume is 8 cubic centimeter for this. Something to remember, 1 liter is 1 cubic decimeter. 1 liter is 1,000 milliliters. That's what we need to know. And 1 milliliter is 1 cubic centimeter, the same thing. And in hospitals, usually they use cc, which stands for cubic centimeter. Now, how do we convert centimeter square to meter square? Now, we know that 1 centimeter is 10 to negative 2 meters, right? It's 1/100th of a meter is that. So, for example, if you want to convert 4 centimeters to meters, then you will have 10 to negative 2 meters over 1 centimeter. Centimeter will cancel out, and your answer will be 4.0 10 to negative 2 meters. But we're not converting meters, centimeters to meters. We want to convert the square, the area. So in that case, if you want to use that, then the relationship here, 1 centimeter 10 to negative 2 meters, so you have to square it. This is different here. So the reason is because this is centimeter square, and if you take square of this relationship that we just found here, 1 centimeter is 10 to negative 2. So that's the relationship between those two, conversion factor. And so that will be this part here will be, so let's write 4 again. So this will be, you multiply this by that, 2 times negative 2, that will be negative 4, and meter will be squared, and centimeter will be squared. So 1 will be squared, but 1 square is still 1, so we don't worry about it. And now you got this one after you square the whole thing. And so now centimeter square will cancel out, and your answer is 4 10 to negative 4 meters square. So the that is what we have. Now this one here, I don't get too much space here. So nanometer and centimeter. So centimeter is, let's do centimeter is 10 to, centi is 10 to basic 10 to negative 2, and nano is 10 to negative 9. So the difference will be negative 2, negative 9, and it will be 10 to 7. So 1 centimeter equals to 10 to 7 nanometer. So we can use that. We can start with here what is given, 250 nanometer cubed, and we write the relationship here. So nanometer gotta be denominator, 10 to 7 nanometers, 1 centimeter. And so nanometer, before we cancel out, we can't, of course. This is cube, this is, so we have to take cube of this portion here. And so again, 250 cubic nanometers. And here, cubic centimeter, 1 cube still 1, so it will be, the unit is cubic centimeter. And so this exponent here, you multiply 3 by 7, so it will be 10 to 27, 21, and the unit will be nanometer cubed. So now we can cancel out the unit, and so that will be your answer will be 250. So this 10 to 21, you can go up, changing the sign, 21, and the unit is cubic centimeter. Now, if you want to, of course, convert this to the metric system, so in metric system, this number here has to be between 1 and 10. So now it is 250, it is greater than 10. So we can move the decimal point to the left twice. So it will be 2.50. And when you do so, you will have to increase the exponent by 100. So that means 21 plus 2. So you got 19 cubic. So that is your answer. Let's see what else we have. Converting between units for a small home office with a size of 250 square feet, a window air conditioner unit with a capacity of 6,500 BTU, that's a unit per hour, is recommended. So how many watts of energy does this unit use? So this is basically a simple conversion between the English system, a BTU, to watts, which is joules per second. And so we have to start with what is given, 6,500 BTU, and the conversion relationship between BTU and joules, we will convert it to watts is joules over second. So first we will convert BTU to joules, and 1 BTU, that is given, of course, you don't have to memorize it, is 1055.6 joules. That is the conversion factor between those two. So BTU will cancel out. We're not done yet because it's asking for watts. Watts is joules per second. So we already have joules left. So we have to, of course, here per hour. So we forgot hour here. And if we convert hours to seconds, now you will have, so seconds has to be here, hour has to be here. And of course, 1 hour is 3,600 seconds. And so hours will cancel out. So what you got is joules per second. That is what we're looking for. And the rest is just the math. 6,500 times 1055.06 divided by 36. And you come up with 1905 joules per second. Now, joules per second, you can write as instead of joules per second, you can write watts, double, capital double. So that is that. Another question here. A car maker claims that his car is the world's fastest and most powerful convertible. And so what we know about the car is that as producing the engine producing 1817 horsepower. So A, how many joules per second, and B, how many calories per hour are produced by this car's engine here. Again, this is also a conversion. Horsepower, we go from horsepower to watts. Basically, joules per second is watts. So we start with 1817 horsepower, HP, and so 1 horsepower is 745.77 joules per second. That is a relationship between horsepower and joules. So if you do the math here, horsepower will cancel out, and you just do the math. 1817 times 745.700, so that is 1.355 10 to 6 joules per second, or you can use watts. And or if you convert it to kilowatts, it is 1355 or 1355 kilowatts. And the B, the calories here, since we already found the joules, we have the watt. So watt 1.355 times 10 to 6 joules per second. We can first convert joules to calorie. The calorie is also the unit for energy, and there is a relationship between calorie and joules. So 1 calorie is 4.184 joules. So now joules are gone. Now we got calorie per hour, and so if we convert the second to hours, we know 3600 seconds is 1 hour. Now seconds are also gone. What is left is calorie per hour. And now what you do is just multiply this by that and divide it by 4.18, and so you come up with 1.166 10 to 9 calorie per hour. A simple conversion. So this is the last example. It's been almost 50 minutes, but at least we're making progress here. Each day, 280 cubic miles of water evaporate or transpire into the atmosphere. So how much is this volume in cubic kilometers? It's conversion from cubic miles to kilometers. Again, we always start, we got continuation, but let's first deal with this first part. We got 280 cubic miles. And so 1 mile is 1.609 kilometers. We have that. And so we open parentheses here. So mile has to be denominator. 1 mile is 1.609 kilometers. Now because this is cube, so we have to take the cube of everything, the whole thing. And so that will be, let's move to 80 cubic miles. And that 1 point, if you take the cube of 1.609, that means you multiply 3 times by it, so it will be, you come up with 4.166, and the kilometer also becomes cubed. And in denominator, you take cube of miles, it is miles, cubic miles. Now you can cancel out those two, and then you multiply these two numbers here, 280 times 4, so you come up with 1166.5 cubic kilometers. And if you want to convert it to metric scientific notation, and so you move the decimal point to the left 3 times, that will be 1.166 or 167, 167, no 6, that we keep it even. So it goes, it stays at even if it is the last digit is 5, and 10 to third cubic kilometers. That is your answer. Yeah, so you convert that's almost 1166 cubic kilometer. That's a lot of water, of course. That's each day. Now the second question is, how long would it take for all water supplies to evaporate if atmosphere did not have a troposphere where temperature drops and condenses vapor? You see, the water keep evaporating each hour, each second, each minute, and each day 280 cubic miles water evaporates. Now, and what happens is cycle. We got the cycle. It goes up there about 7 point some miles, 7-8 miles, and it condenses. It comes back. What if we didn't have that layer, that cold layer? It would go deep to space, deep into space, right? And it would disappear. So question is, how long would it take this much water? We got 332.5 million cubic miles of water, including everything, oceans, seas, and other water. That is what we have. So how long would it take to evaporate? So basically simple. We have 332.5 times 10 to 6 cubic miles, and so and we know that 280 cubic miles per day. So these miles will cancel out, cubic miles, and now day will go up. So you will have 11875 days. That's a big number, and so we can convert. We know a 1 year, 365 days is 1 year, and so if you do the math, divide that number, that's 1,187,500 days, divide by days, so you come up with 3,253 years. So all of our water will evaporate in 3,253 years. So finding water on Mars, for example, is not enough. So you would have to have a system to keep that water from evaporating and disappearing completely. It's almost 1 hour. Hopefully it is helpful. We will continue on other sections of the chapter.